This is Lab 5, Choose Your Own Adventure, and I chose to do a falling slinky. So I chose to analyze the motion of a stretched slinky dropped from static equilibrium, and I did this to demonstrate the effects of gravity and drag force on the motion of the slinky. And then I developed a computational model of the slinky motion and compared to the observed. And just an overview of the results is that the bottom of the slinky stayed stationary until the slinky returned to its equilibrium length after being dropped initially. So here are the physics concepts and formulas. So the main concepts were gravitational force and drag force for a falling object. So in this case, gravity and drag force were the only forces acting on the slinky, and they were acting in opposite directions. And acceleration of the slinky is caused when these forces are not balanced. So when the force to gravity is greater than the drag force, it accelerates in the downward direction. But if the forces are balanced, then F net is 0 and there is no acceleration. So this also demonstrates Newton's second law. The acceleration is force over mass. And like I said, F net equals 0 means there's no acceleration in the downward direction. And then other formulas I used were the position update and velocity update, and then F net was the force of gravity, drag force, and the spring force added together. So I assumed that the force of gravity remained constant, and then I also assumed that the drag force was proportional to the square of the velocity. And then here I have models of two scenarios. So the first one on the left, you can see the drag force and the force due to gravity are balancing each other so that there's no acceleration and the speed remains constant, and F net equals 0. And then on the right, the force of gravity is greater than the drag force, and because of this, F net does not equal 0 because they don't balance each other, and so there's acceleration in the downward direction, and the terminal velocity is greater than the initial velocity. And this is the tracker analysis. I upload the video and then track the center of mass as the slinky fell. And then for the computational model, you can see here for the velocity update and position update formulas, the code used, and then as well as the force of gravity equation and drag force. And then on the right, you can see the picture of the code. This just set all the initial conditions. And then here I have actual code to generate the model as the slinky fell. And then here's a comparison of the model generated by the tracker data, and then the one I made in GlowScript using my computational model. So the blue is the observed motion, and then the orange is theoretical computational motion. So as you can see in the previous slide, the computational model and the experimental were very similar. So the bottom of the slinky remained motionless until the top of the slinky fully closed and the slinky returned to its equilibrium length, and the spring force pulling upward balanced the gravitational force downward, and acceleration did remain constant as the slinky fell. So this is, as stated before, an indication that the F net was 0 and the forces were balanced. And like I said, the tracker model and the computational model were very similar. So for my potential what if, first I asked what if the model predicted terminal velocity, that is the computational model, and the answer is yes, since this model does take into account drag force. If the model didn't take into account drag force and only took into account the force of gravity, for example, then it wouldn't predict the terminal velocity. But since it does take into account drag force, and in this scenario, drag force balances gravitational force, so the speed is constant, and therefore we can predict the terminal velocity. So it would be the same as the initial velocity because there's no acceleration. And then for the second what if question, I said, what if instead of being dropped, the slinky was thrown down? So this kind of goes back onto how we can predict the terminal velocity. Since there was no acceleration in the downward direction, the velocity remains constant, and initial velocity terminal velocity is unaffected by the initial velocity. Terminal velocity is determined by the mass and shape of the object. So in this scenario, the drag balances the gravitational force, so the model does predict the terminal velocity. And that's all.